Hey everybody, so this is the first video with in the thermodynamics class where we're going to kind of pretty much start off the basics of the concept of thermodynamics. So I had mentioned before that the main idea with thermodynamics is that we're going to take a step back and reevaluate our understanding of thermodynamics, of thermal energy of gases, how they interact, except instead of looking at it at a macroscopic level, pretty much a reactionary thing, we're going to actually look into it at the microscopic level. Um, and we're going to end up needing to pull out some statistics and some those types of methods that you would use in statistics. So the main thing with thermodynamics is that we're pretty much coming up with relationships between work and heat. Work being the mechanical part and heat being the thermal part, hence the name thermodynamics. So taking heat or thermal energy and getting something to move and vice versa. Um, so like I said before, what we want to do is try to come up with uh, an understanding of what's going on with the gases and looking at the individual particles that are making up these gases in order to actually understand what's going on, what's causing the heat, how is the heat transferring, all that stuff. Um, Now, because of the fact that the particles, for the most part, contain millions upon trillions of particles, we're going to have to do infinite sums and treat this using statistics. So that's kind of the whole idea. Now, we're going to basically start with the simplest case of what's called a binary model system. Binary meaning that there's only two possible states that each particle can be in. This is kind of why I used the phrase quantum before, because we're looking at the states of the particles. So the two states that we're going to look at for now are that the particles can either spin up or spin down. Um, and that's pretty much it. However you want to think about it, on, off, up, down, true, false, anything like that, that's what's going on here in this binary system. Now, because of the fact that particles and atoms do have a magnetic moment represented by a little m, what we're going to say is that essentially the magnetic moment for each particle or each atom can be plus m or minus m because it could either spin up or it could spin down. Um, Now, what we're going to do is because we don't want to jump straight into trying to figure out what's going on for millions upon billions of atoms. Instead, what we're going to do is we're going to first look at a few particles, a small case. We're going to use a little bit of algebra for those cases and pretty much a brute force it elementary style. And then we're going to try to figure out a pattern that we're noticing with those small cases and use that to kind of build up to the bigger cases. Now, when we do these small cases, we're actually going to identify each particle as a specific individual unique particle. So they're all going to be given a specific number, if you will. We're doing this just so that we can kind of keep track of everything and be able to, as they say, count the states, as you'll see in a second. Now, the best way to kind of visualize what we're doing here when we're talking about, this whole spin up, spin down, binary model system and counting states is just imagine that instead of talking about particles and their spins up and spins down, because who can even visualize that? What we're going to do instead is visualize, or what you could do instead is visualize something like a parking lot where each of the spaces is numbered. Um, you can only have a car in a space or it could be out of the space. That's it. Those are the two states: full, occupied, or unoccupied. And you'll never have a case where there's a car covering two spots. We're going to pretend at least that everyone in this imaginary world actually can park properly. So we're going to start with this first case. So here is a scenario. We have 10 particles all randomly going up and down. There's no real rhyme or reason to it. So what we say is that, well, since there are 10 particles and each particle can be in one of two states, that means that particle 1 could either be up or down, particle 2 could be up or down, so on, all the way to the 10th one. So if I want to know how many possible states I could have for 10 particles, it would be 2 times 2 times 2 times 2 all the way up to 10. Or it could be simplified as 2 to the 10th power. So number is going to tell me how many possible states I can have. And this scenario is just one of those 2 to the 10th possible states. That is an extremely large number. 1,024 possible states. So this scenario, if this kind of goes into the idea of probability, that this is one of those 1,000 plus states. So if I had a set of 10 particles and I just randomly let them orient themselves, and assuming that each orientation is equally likely, that particle 1 is equally likely to point up as it is to point down, and the same for all these, then that means that the probability of me actually getting this specific case can be said to be 1 over 2 to the 10th. 1 because this is one specific scenario, and this being the total number of scenarios that are possible. If I use this, that basically means that I have a 1 times 10 to the negative 3, I believe, percent chance of getting it. All right, so using that idea, the fact that for 10 particles, the total number of states was 2 to the 10th, what I can then say is that it's clear that if I had n number of particles, then the number of possible arrangements should be 2 to the nth. As we said before, each particle had a probability or had two states, so the total number of states would be the product of all those 2's, and that's where I get 2 to the n. Again, we're going to pretty much, in this first part at least, look at small cases and use that to build up to the bigger cases, to the more real life cases. Now, because we're actually trying to relate this more to a physical aspect, what we can say is that each of these up arrows is representing a magnetic moment of plus m, and all these down arrows represent a magnetic moment of minus m. Well, because this is a complete system, I can find the total magnetic moment, which we're going to label by capital M, by adding up all the ups and all the downs. Another way of thinking about this is, you can think of this as just being plus 1 minus 1, and then seeing what the total number is at the end. Or you can think of this almost as like a difference between or the excess of one amount versus the other. If you want to try to use this in a non-physics sort of way. Now, the maximum total magnetic moment we can get is if all of these are all pointed upwards. So we'd end up having n particles all with a magnetic moment of plus m. Or I'd get that the total magnetic moment was just nm, a positive value. Likewise, the minimum total magnetic moment I could get would be if all of them were pointed down with a magnetic moment of negative m. So for n particles, each with a magnetic moment of negative m, it would be the product negative nm. All right, this is going to play a part in a second. All right, now let's go back to kind of looking at small cases. Now we're going to consider a case where we have three magnets. Now, using the equation, I can immediately tell that immediately know that the total number of possible states that I have would be 2 to the third, which would be 8. Now, I can then think about all the different combinations or setups that I can get. Well, one case would be all three of the magnets are up, which means that the total magnetic moment would be plus 3. So this is one scenario that would get us this other case. Another thing that we could have is instead of having 3 magnets up, we could have 2 magnets up, giving us a total magnetic moment of plus m. Now here, we don't have just one scenario that would actually satisfy this. We have 3. The first 2 could be pointed up and the last one's down. The outer ones could be pointed up and the middle one's down, or the last 2 could be pointed up and the first one's down. All 3 of these give us this scenario of 2 magnets up with a total magnetic moment of plus m. Like continuing with that concept, I could flip this and say, well, what if there's 2 magnets down? Our total magnetic moment would be negative m. Once again, we have 2 scenarios. Oh, sorry, not 2, 3 scenarios. And then the last case would be 3 magnets down, which only has one state that satisfies it. So with these 3 magnets, there are a total number of 8 different possible combinations that I can make. However, there's only 4 unique values of these values of m. Now this leads, I've been trying to refrain from using these phrases, but what this is going to lead into is what we call a microscopic state scenario and a macro state scenario. So here, this is our micro state scenario where we're looking at all the individual states, where we're looking at, every single little itty bitty particle and what they're doing and all together. So again, there's 8 different ways that these 3 magnets can be aligned. This is the microstate interpretation. The macro state would be the overall effect. Well, from my point of view, I technically wouldn't be able to see this, again, assuming that these were microscopic, I wouldn't be able to see this, but these are the things I'd be able to measure. I'd be able to tell if the total magnetic moment was plus 3. I'd be able to tell from my point of view if it was plus m or minus 3m. So these are what we call the macro states, essentially the total effect, the overall effect that you end up getting. So you're going to want to understand this difference of relationship. So this would be in the thermodynamic state sense, this would be like the individual energies of the particles, the speeds, the velocities, all that. While this would be things like the pressure that we end up registering, or the temperature, or the heat transfer, or something. So this would be what we could actually measure, and then this would be, what's actually going on that we aren't able to actually see. All right, so what I want you to do is I want you to pause this video and work on this question real quick, trying to use what we just learned before, and we'll go over it in a second. All right, so they want us to consider having 4 magnets. And they want us to pretty much did what we just did before. First, figure out the total number of states, and then find how many unique values of m there are. All right. So the first one is fairly easy. I mean, we have an equation for that. There's 2 possible states for each magnet. So it's just 2 to the n, which is and n being the 4 magnets, we get the total number of states is 16. All right. Now we go to part B. So how many unique values of big M are there? Well, the only real way right now that we can do it is, once again, taking the elementary route, brute forcing our way through it by just writing all down the combinations down. So the first one is we can have M being plus 4. That means all the particles are pointed upwards. Plus 2 would be 3 going up and 1 going down. We could have 0, where there's equal numbers going up and down, 2 and 2. Negative 2 being 1 up and 3 down. And then negative 4 being all down. So what we end up getting is that there's a total of 5 unique values for M. Now, with this, when we have small numbers, this is something that we can easily do. It doesn't take that long, and it actually is kind of fun going through all the scenarios. But as we start getting with bigger and bigger numbers, we're going to want to kind of come up with something a little bit easier for us to do. So this kind of goes back to what I said before about how what we're going to want to do is try and take our understanding of what's going on here and relate it to what we've done before. So far what we have is that when n equaled 3, we had 4 possible states. When n equals 4, we have 5 possible states. Now, if we tried n equals 5, we could see, well, how many states that would be. My guess would be it would be 6, because it seems like whatever number n is, the total number of values for m would be 1 more than this. And that seems to make sense. If you want, you can try this yourself and see, would 6 work? Well, would 5 work and get us 6 total values? Well, really quickly, I can see that all of them up would be plus 5. 4 up and 1 down would be plus 3, I believe. I would get plus 1 for 3 up and 2 down. And then each of those is mirrored. So that gets me, another 3. So 6 altogether. So we can see that idea. So we're going to, using those examples, these are the two things that we see. We see that the value of m is always going to end up being a difference of 2. So if you didn't notice that, you could see it here. Plus 4, plus 2, 0, minus 2, minus 4. And if we go back to this one, plus 3, plus 1, minus 1, minus 3. So that's another thing that we could do is, if we want to do this really quickly, we can just identify the very first scenario, all of them being up, so it would be nm, and then just keep subtracting 2 from that coefficient until we get the negative of that number. And that would also be a very quick and easy way of figuring out how many total values there are. And this makes sense, the fact that the difference is always going to be 2, because not only is it losing a positive, it's going to be gaining a negative. So it ends up doing almost double duty on that effect. So instead of being 4 plus 4 for all 4 magnets pointed up, it loses 1 of them pointed upwards. So now it's 3, but then one of them is going down, so that's canceling out another one of the ones pointed upwards, getting us that plus 2. So here the kind of goes back to what I was saying before about how we can just identify what the very first and max value for m is, and then just see how many times we could subtract 2 from it until we end up getting the negative of that number, the minimum value. The other thing that you should have noticed was that and this is what I said before about how the number of values for m, the unique values for m, is always going to be one more than the number of particles that we have. And that basically ends up saying n is equal to n plus 1. So the number of values for m is always going to be n plus 1. All right. So because of the fact that we're usually going to be dealing with cases that n is significantly greater than 1, what that basically ends up telling us is that the total number of microstates that we can have will always be significantly higher than the total number of macrostates we end up seeing. Just like we saw before, what we'll end up getting is that there are going to be multiple cases of arrangements that will satisfy essentially the same setup. Now, before I continue, I do want to point out that we're going through this concept right now. We're kind of anyone who's learned about statistics will know that there are better equations that we can use to kind of quickly get everything. However, the reason why we're going this route is mainly because we want to try and think of a good way of explaining it. We want to try and develop the concept from the foundation. So a lot of times when you're doing stuff in physics, what you want to try and do is break it down to its core parts. And that's what we're trying to do right now, is try to like go back to basics, figure out how everything plays a part, not really taking into account the whole static stuff, statistics stuff, until we start getting into the more complex things. And the other thing is using a lot of those statistics, things like choose one or pick one, like NCR and NPR, for those who actually know what I'm talking about, the permutations and combinations. That would be like using a battle axe to cut a slice of cheese. You know, that's really good when you have very complex setups of, there are 6 different combinations and we're only going to be picking a few, and mixing that, like maybe if you're doing dice rolls or deck of card things. Yeah, that's something that you would want to use that for. But we're talking about up and down, flipping coins. We don't really need to use that crazy thing. We're going to end up using, some of these more antiquated and less effective cases. If hopefully that makes a little bit more sense. All right, so yeah, this just kind of goes back to this whole idea that this term, the number of microstates, explodes clearly exponentially or logarithmically, whatever you want to say, so quickly compared to the number of possible values of m, which would actually go up more linearly. So for n equals 10, what we'd end up getting is, a little bit over 1,000 possible states, but only 11 unique combinations. And this goes back to what I was saying before about how this is referring to the microscopic states, and these are the macroscopic properties. I apologize that I always get those words mixed up. It's a tongue twister for me. All right, so here, what we want to do is we want to actually come up with a way of figuring out how many states, how many microstates are actually related to a value of m. So if you remember when we did the scenario of the 3 magnets, going up or down, I had written out all the scenarios, and I said that there were 3 cases that pertained, or 3 different combination of states that pertain to one value of m. Well, we want to be able to do that, but we don't want to have to go that type of route where we have to write everything down. Instead, we want to try and come up with a number that will allow us to use large numbers. I don't want to have to write everything out for 100 particles. So instead, we're going to end up coming up with this function, what we're going to end up calling the multiplicity function. Now this is going to be denoted with the term g. Quick side note, I'm using g because this is the term that they use in the textbook. If you look online for the multiplicity function, you'll notice that the equation is slightly different. I feel like they use a capital omega in some cases. This is one of these weird topics where the symbology changes drastically. You know, you search multiplicity function for some help, you'll notice that almost every symbol that they use is different. Same thing with some of the symbols that we're going to be using for things like entropy. It's going to be completely different than what you might find online or from other sources. So just wanted to throw that out there for those who try to look for help online and you start seeing all these weird symbols that you haven't seen before. It's because the book that we're using writes everything a little bit differently. All right, so what we're going to say, we're going to start off saying that n is going to be so large that it's going to be an even number. You know, think something like, again, billions and billions, 1 mole of molecules, so large, it's, for all intents and purposes, it's going to be an even number. We're going to ignore the fact that there might be one particle, you know, in and out of that scenario because it's not really going to matter. So of all the particles can either be in one of two states, n up or n down. So what we can say is that the number of particles that are pointed up is going to be half the total number of particles plus s, where s is going to be almost like a excess number. And that also is going to give us this, that n down is going to be equal to 1/2 n minus s. We can see this makes sense because when we add these, the number of particles pointed up and the particles pointed down should be equal to the total number of particles. N should equal to n up plus n down. And what we get when we add n up and n down is that the s's drop out and this combines to n. So yeah, it makes sense. So that's good. And this is kind of one of the reasons why we said that n is going to be so large that it's an even number, because technically this equation wouldn't work if n was something like 5. But also you'll notice that it ends up simplifying, so we don't even have to worry about that. Now if we take the difference between these, we end up getting 2s. So 2s is going to be referring to the difference in the numbers, the excess of particles up or the excess of the particles pointed down. So they use the term spin excess for this. Now this is a very important thing that people can get a little tripped up on, is they think that the s would be the spin excess. It's not, it's 2s. Sometimes you might actually see the book ask for the half spin excess. When they're saying that, they're actually asking for the value of just s by itself. But when you are asked for the spin excess, or how many more are pointed up versus how many that are pointed down, the difference between these numbers is going to be equal to 2s. All right. Yeah. So again, number going up. So a good example of this is that this would have a spin excess of 2 because there are 2 going up and 0 going down. So it's 2 for 2s. And then likewise, if we asked what the half spin excess was, then we would say that s equals 1. This would have a spin excess of 0, another one of spin excess 0, and this would be spin excess of -2. We can actually relate this back to the whole total magnetic moment and say that the values that we can have would always be 2sm. That whatever the spin excess is times m are some of the values for big M. that we could have. And again, we could see that for all the other cases. All right. So kind of going back to what we said before, each of the particles, we have n particles. They can either be pointed up or down, and these are all the different states. If we drop the subscripts, and saying that for the most part, since each particle pretty much is going to behave the same way essentially, where there's two equally probable states, we could just simplify this and treat them all the same by just getting rid of those subscripts, and then we can combine this all together to just say that this is essentially just up plus down to the nth. So again, total number of states. There are two possible states to the nth power. So another way that we can write this, if we want to kind of, expand this binomial function, is that essentially we have these scenarios. We could have two particles pointed up, and there's only one case that's like that. We could have one particle up and one particle down, where there's two cases like that, and then there's two particles going down. So the reason we're going to do this, if you haven't started to see kind of the thought process that we're doing right now, is by simplifying this scenario into this function, we can then relate this to a binomial expansion. So if you recall things like x plus y to the, x plus y to the n power or the third power or the fourth power, and when you expand it, you get that I don't want to call it quadratic, a polynomial function, where you have all these exponents to the top, and you have these coefficients, and there's always the same pattern to the coefficient. That idea is what we're going to end up using, because there is actually a function that's going to tell me what this specific coefficient is for this specific term. All right, so when it was to the third power, the expansion would look like this. Again, very quick and easy way that we can actually come up with the number of states for every macro state. So one macro state, one micro state. This one macro state, three micro states, so on and so on. All right. So yeah, the multiplicity function is going to end up being essentially the coefficient equation for a binomial expansion. All right, so if you recall from algebra, when we had the binomial expansion, the equation in its long form looks something like this. That essentially we'd have x to the n, all the particles in this case pointed upwards. One less particle pointed upwards and one of them is pointed downwards, two less pointed upwards and two pointed downwards, so on, until we have all of them pointed downwards. Then the equation, this can be simplified as the sum for I equals 0 to n of this function. Now, replacing these terms like x and y with number up and number down, what we end up getting is this. So x and y are replaced with the ups and downs. We're going to replace these I terms with this, the half spin excess numbers. And now our function looks like this. This term is actually going to be what we use to figure out how many possible states are available for a given macro state. So this is our macro states. How many particles are spinning up, how many particles are spinning down, and then this one it being the coefficient that's related to that specific case. This is good because what this means is that we don't even have to really worry too much. If we want to simplify this, we have 50 particles, Well, we just plug in 50 factorial over 1/2 of 50 plus s, 50 minus s, where s is going to be whatever that half spin excess is between the number going up and the number going down. So what we're going to write is that g, which is our multiplicity function, which is based off of how many particles we have and the half spin excess, is given by this equation. Or another way of writing it in a slightly simpler way would be given like this, where this is just the number of particles in one state and the number of particles in a second state. Typically, when I have a very important equation, I tend to bold it and give it a special color so that it stands out. So this ends up being the first major equation in this topic. All right, so this, like I said, is our multiplicity function. So going back to that whole summation that we had, we can basically just place this multiplicity function in for that whole big mess that we had before. Now, of course, one thing that we should note is that when we sum the multiplicity function across all the values of the different half spin excesses, we should end up getting 2 to the n, the total number, which makes sense because this is just the coefficient, the number of states in different scenarios, in different combinations. So the sum of all of those possible combinations should give me the total number of states. All right, I'm just going to end the video right here for a second, and we'll continue on in the next video. We'll do a quick little practice using this equation, and then we'll continue on and talk about how we can simplify this multiplicity function in in an easier way for larger numbers. All right, see you in the next one. If you have any questions, let me know.